Hi, everyone. Happy to see so many familiar people. Welcome all. And happy to see a lot of new people. I see that our community grew over the last year. That's very cool. So whoever doesn't know me, I'm Sasha. I'm leading the research in Aptos Labs, and I want to talk to you about the Aptos tech. Recap what we already achieved in the last few years, and share with you the exciting news for the future. So it all started 3 years ago when a group of us left Novi, left DM, to start building Aptos. Our starting point was what was back then considered the state of the art, a pipeline and blockchain architecture. So if you see a life of a transaction, pretty much the same in all blockchains, transaction goes through consensus, execution result certification, and committing to storage. So every transaction needs to go all these stages. So the reason we're pipelining, the idea behind pipelining, is because we want to utilize better the resources. For example, when a block is being committed to storage, the next block can be certified, the next block can be already executed, and the next block can be already in consensus. Because each one of these stages require different resources. For example, consensus is networking heavy, while execution is CPU heavy. We can do all of this in parallel and increase throughput. So I also want to mention that back then, for consensus, we used JoltN. For execution, we used BlockSTM. At the time, both of them were state-of-the-art, developed by the Aptos researchers and engineers, and later adopted by many, many other major blockchains. So moving on, in 2023 was the year when we pushed throughput. We introduced quorum store in order to increase our throughput by eliminating the bottleneck of a leader in a leader-based consensus. Before, without quorum store is a parallel data dissemination. So without that, our consensus was limited by the ability of a single leader to disseminate data. Basically, the leader had to propagate the data to the entire network. With quorum store, we could do it in parallel. It's a sequential component we added before consensus, where all validators were disseminating data, and the leader, all he needs to do is to propose small metadata blocks to refer to this data. So this by itself gave us 10x throughput for our consensus mechanism. All right. Moving on, in 2024 was the year where we really pushed latency. We took our JoltN protocol. Back at the days, it was 5 message delays, and we reduced it to 3 message delays. 3 message delays is the theoretically optimal. So in 2024, we achieved the theoretical optimal latency for consensus. This year, in 2025, is then we really pushed our performance, our blockchain performance to the limit of what is possible based on the speed of light. Now, we introduced Raptor and we introduced Aptos. And I want to quickly go over them. Raptor is a consensus optimization. And if I remember just a few slides ago, I told you that with quorum store, we could scale throughput by 10x. But the problem with quorum store is that this is the component we add sequentially before consensus. Remember, we had the stages life of a transaction. So a transaction first needs to go to quorum store, then consensus. This is a penalty, latency penalty. With Baby Raptor, what we do is that we took quorum store and we merged it into consensus. We piggyback the parallel data dissemination on the consensus logic. So by doing that, we're able to cut our end-to-end latency by an entire round trip, which is very, very significant. All right, Velociraptor is another consensus optimization. But here we're focusing on the block time. Before Raptor, with JoltN, we're able to propose a block every round trip. We need a little bit more technical. We had to wait for the previous block to be certified. It usually takes a round trip before proposing the next block. With Velociraptor, we can optimistically propose a block every message delay, every message hop, one block, basically cutting the block time by half. No, these are my slides, not this. Interesting. OK, so Aptos is a new architecture for our pipeline blockchain. I remember these slides from before. It looked a little bit, the diagram looked a little bit different. The transaction needs to go sequentially from all stages. Yes, it was pipelined, but it had to go through all the stages. Basically, the pipeline architecture that I mentioned before improved throughput, but it didn't improve latency, because transaction had to go sequentially through all the stages. What we do with Aptos is very cool. We are able to optimistically do execution, certification, and commit while doing the consensus. We're basically shadowing all this latency with the consensus. So by the time we finish consensus, by the time the block is ordered, we already executed it, we already certified the result, and we already committed it to storage. So in the good case, in the optimistic case, which is most of the cases, our end-to-end latency is equivalent to our consensus latency, which, as I told you before, is already optimal. It's 3 message hops. It's a theoretical lower bound. We cannot go lower than that. So really, over the last few years, we have optimized the pipeline architecture, throughput and latency. We have optimized every component, and our entire stack is fully optimized right now, to the point where it's really limited by the speed of light. I don't know how much farther we can go like this. And let's see the numbers. Let's see how all these cool optimization translate to the numbers. So if you remember last year, before many of this optimization even roll out, we demonstrated the record. Up to date, it's still the record, the still Web3 record, 326 million transactions per second in a single day. During this time, we were able to peak almost 20K TPS throughput on mainnet, which is quite nice. As for the finality, there are 2 numbers. There are 2 important numbers. The end-to-end finality, from the time a user submits a transaction to the time the transaction is confirmed, and there is the block time. So if you go to Aptos Explorer today, you will see that our finality, the true finality, is 400 milliseconds. And this is before we fully rolled out Aptos. So expect in a few weeks, we're going to let you know, we're going to tweet about it, don't worry, this number to go much lower. Block time, the same. 85 milliseconds today, probably 4 or 5x better than any other blockchains. And this number is going to go much lower, probably around 50 milliseconds when we finish rolling out Velociraptor. Also, by the end of the year, all this optimization will be in. And now we want to focus on the next thing, which is building the best infrastructure for trading, because we believe trading is the future of blockchains. And today I'm excited to share with you our roadmap for the global trading engine that we are building. On a nutshell, we aim to have 6-level latency and throughput, complex throughput. By complex throughput, I mean not just simple peer-to-peer transactions that people like to brag about. You know, we do this, we do that. No, I'm talking about complex trading logic. We want to do very low latency and very high throughput of these transactions. We will provide built-in MEV protection with on-chain automated logic. And finally, we're going to introduce namespace to allow apps and close partners more control of their block space. So let's start with the millisecond latency. I'm excited to share with you the Archon architecture, which is going to be our new consensus architecture. It's going to work as follows. So I told you before, our consensus is geo-distributed. 3 message hops, very optimized. We can't go much from here in terms of latency. We are limited by the speed of light. But we do want our millisecond latency. We want to be able to support these trading use cases. So what are we going to do? We're going to be creative. Imagine I could tell you that one of these validators is a leader. One of these validators is very strong, very trusted, never lies. It can be a very good leader, very strong networking connections. If we could magically add such a validator, we could make him a stable leader. So when a client communicates with this leader and the leader acknowledges the recipient of the transaction, the client can be safe. The leader will not lie. He will propose. He promised me that's the order. I can trust it. He has a strong connection to the network. The network will not skip this leader. I'm good. I'm getting instant inclusion confirmation, and I have my predictable latency. That's exactly what I need for trading. However, of course, we are in a decentralized world. This is impossible. It's all trustless, right? We cannot have this magical leader. So what we do instead with this insight is that we are going to build this leader. We are going to build an abstraction, a BFT abstraction of that leader. We are going to have a co-located committee. Co-located is important because we really want this millisecond latency. We are going to have a co-located committee to emulate, simulate, abstract, whatever fancy word we are going to use, this stable, strong leader. So internally, this committee will run a consensus. It's going to be very fast. Everything is co-located. And then by doing that, by running this consensus internally, we guarantee that this abstract leader is not going to equivocate, right, under the BFT assumption. And all this committee is going to be collaboratively responsible to propagate the block, the agreed upon block, to the rest of the network. So there is no single crash point of crash, point of failure. In standard consensus system, if the leader crashes, the rest of the network needs to time out, recover from it, and we are losing latency, and we are losing the proposal, we are losing the guarantees. Here, because we have the BFT abstraction, we have the committee simulating this leader, we have much stronger guarantees. So whenever this committee agreed on the next block to propose, the clients can already be assured that this block is going to be included, and they have their inclusion proof. So I wanted to pay close attention to these numbers. With this optimization in place, once we implement and roll this out, we'll have a proof of inclusion every 30 milliseconds, and we'll have a block time every 10 milliseconds. 10 millisecond block time with this new Archon architecture. I'm really excited about that. So we're running BlockSTM v1 for 3 years now. We have a lot of insight. We saw the bottlenecks, and we were thinking hard, how can we improve it? And surprisingly, even though BlockSTM v1 was so good, adopted by so many blockchains, we still managed to come up with an algorithm which was much better. On every possible workload, it is much more scalable. This is because we managed to implement a smarter scheduling and a smarter conflict handling. That's a bit of technical terms, and we are going to publish everything, and everything is going to be more clear with blogs and papers and everything as we usually do. But just to give you a taste, it will also have much less overhead in terms of synchronization and waiting. So as I said today, it's already beating BlockSTM v1 on every possible workload. And the next step for us right now is going to be to optimize it specifically for trading. And the way we design BlockSTM v2 is exactly for that. So we are ready now to go and to really optimize this decibel workload. And today we are at the point that, as we speak, BlockSTM v2 is being productionized. MEV. MEV is a big pain point for like most DeFi protocols, right? And we want to make sure we protect our users. So to this end, we introduce Encrypted Mempool. Remember the life cycle of a transaction? Transaction goes through consensus, execution, certification, commit. MEV, after a transaction is ordered by consensus, this point, MEV is already impossible, right? Nobody can front run if the final order is already committed, right? So what we do, we introduce an encrypted mempool. When a user submits a transaction, the transaction is encrypted. No one can see the transaction. Not the validators, not the other users, nobody. The transaction is encrypted. And then we have a very, very novel technology. So the validators collaboratively can decrypt the transactions immediately when the consensus is done. We are piggybacking the decryption on the final stage of consensus. And this is important, because if we do it before the final stage of consensus, then MEV is again possible, right? The leader can decide to skip this block, to insert some transactions, right? We have to do it. We cannot do it before. And it's also important not to do it long after consensus, because then we'll need to pay a latency penalty, because we cannot execute the transaction before we decrypt it, right? So it's very important that we decrypt the transactions immediately when the consensus is done. And this is exactly what we're doing. So no front running, no censorship, and it's very important to know that decryption is happening on the validators. And this is because we don't need to add any other security assumptions, right? Sometimes you like assume this, assume that, especially for cryptography primitives. No, the same assumption, the secure Aptos network today, the same BFT assumption is going to be the same assumption we use to secure the privacy of our traders. Of course, we'll have to introduce a small latency penalty, but it's going to be less than 10% for encrypted transactions and very minimal for unencrypted transactions. And I just want to mention that if you're really interested, you can go read the papers. This cool feature is based on two recent papers by our team. One is published in Crypto 2025, which is one of the best, maybe the best cryptography conference in the world, and the other one is currently under review. So I encourage you to go and check the details. This is really, really cool. So most other chains are just databases, right? You just submit transactions, change the state, you get a result. We aim for Aptos to become a reactive operating system. What I mean by that, before that, today, if you go today on Aptos, you can submit a transaction, and that transaction can schedule more transactions in the future. Kind of cool, right? You can submit a transaction today, and some logic is going to be executed without you. You don't need to do anything. In a future time, in a future block, you decide. In the future, we are going to generalize it, and we are working on it right now. to make it fully event-driven, which means that you can submit transaction, that transaction will be able to subscribe to events, and when this event happens, the logic is going to happen immediately, executed immediately on the blockchain. This is useful for so many things, but in particular, it's useful to remove on-chain bots logic and allow much more sophisticated on-chain trading logic on Aptos. Last but not least, the anticipated namespaces. Everybody was talking about namespaces. We really believe this is the future. So as I mentioned before, we push the infra to the limit of the general purpose L1. But still, we think that serious big apps, they will never want to come and share the same space. This is because they want control over their things, and they want a guaranteed block space. Also, for different use cases, it makes sense to separate the space and customize environment and execution to their specific needs. For example, we have Shelby and we have Decibel. Shelby is very, very heavy on-chain metadata storage, and it has to be cheap. Decibel requires an ultra-fast transaction, ultra-low latency. And with namespacing, we can achieve both. So to summarize what the future of Aptos architecture unlocks, we'll have namespace architecture designed to connect the decentralized world. We will have centralized speed with decentralized freedom. And we will have automated on-chain finance with built-in MEV protection. This is a lot, I know, and we're building it as we speak right now. The Aptos global trading engine is real, and we are building the best infrastructure to support it.